Hello and welcome again. Today I want to continue making some connections between the reaction profile diagram here for an exothermic reaction and the Boltzmann distribution curve. Focusing today specifically on the effect of an increase in temperature on an exothermic reaction, on the equilibrium position of an exothermic reaction. And we might think of it if we follow Le Chatelier's principle, an exothermic reaction. Heat is produced, heat is a product. So therefore, if we increase the temperature in this exothermic reaction, then the system would behave to consume that heat and to move back towards the reactants. And we would know that using LCP, that the reverse reaction is favorable. But of course, as we've said before, there's no deep conceptual understanding. There are no connections in that kind of approach to the reaction profile diagram. And today, of course, we're going to emphasize how this reaction profile diagram can connect to the Boltzmann distribution curve. So let's start. Here we have the forward reaction. And of course, in an exothermic reaction, the products have a lower energy level than the reactants. And it's this difference in energy that accounts for the fact that there is a release of energy in the exothermic process, which gives a negative enthalpy change or a negative delta H here as shown. But if we were to have this reaction happen at one temperature here, T1, and to put the green activation energy barrier here with this short arrow and the blue activation energy barrier for the reverse, this blue arrow, and we were to quantify these energies here on the x-axis, you would see that EA for the reverse is way down with this amount of energy, EA for the forward is way up here. And then the number of particles that would be able to cross that barrier is indicated here. This blue plus this red would be everything that can cross that barrier from this side over this. But just this red here would be everything that could cross this barrier here. Because as you could see, just by inspection, this barrier is way bigger. It requires more energy. But here, mathematically, you can calculate the area here, of course, under the curve by integration. You could calculate all of this and you could show that effect. But here's the thing about the Boltzmann curve. When you move from T1 to T2, the curve takes on this shape. And here you can see now that at T2, all of these particles here plus this minus this would be going over the green barrier. But what about the blue barrier? It will be all of these red plus all of this extra bit here. So immediately you can see just qualitatively that this is going to go up significantly. And as this goes up significantly, it's going to have a much greater increase going this way in the number of particles that can go versus the number of particles that are going to have an increased energy going this way. And if you were to actually integrate the area under the curves and calculate the area, you would be able to prove that as you increase the temperature in an exothermic system, you provide more advantage or relatively greater probability of particles on the product side crossing over to the reactants. And of course, you can always apply Le Chatelier's principle to help you confirm.